The next section in the textbook is the temperature and the rate. So we saw in the very first video the fact that depending on the temperature, which was the first part where he had the 4 Erlenmeyer flasks that when he shook turned blue, that the higher the temperature, the faster the reaction rate changed. And so this happens to be because the rate constant is temperature dependent, which I've mentioned in all the problems because they do give you a temperature when they give you a rate constant. So how does the rate constant change with temperature? So this is a figure out of the textbook that shows potassium permanganate and oxalic acid. And so it's going from purple to clear. And so one is at room temperature, the other one is being heated. After 10 minutes, the one that's heated has gone to clear, and the one that's at room temperature is still purple. So the warmer it is, the warmer the solution or the reaction area is, then the faster the reaction goes. The reason that the temperature has an effect on the rate constant is something called collision theory. Basically, it says that for a reaction to occur, 3 things must happen. First of all, the particles must collide. They must have sufficient energy, and they have to have the correct orientation. And 2 of these 3 are temperature dependent. Okay. You can click here to watch this video if you'd like to, and it shows you an animation of that. So this is the equation that basically relates the rate constant to the collision theory. So you have 3 variables here, z, which is the collision frequency, so they must in order to collide. So this is how often do they collide. F is the fraction having sufficient energy for a reaction to occur, and P is the fraction occur with the correct orientation. So Z and F are temperature dependent because that the higher the temperature, the faster the molecules move. The faster they move, then the more likely they are to collide. So that's why Z is temperature dependent. Also, the faster they move, the more energy they have. So F is also temperature dependent because if they're moving faster, they're going to have more energy and therefore have a higher fraction that has sufficient energy. And then P, which is the orientation, is independent of temperature because the speed that they move and the energy at which they move doesn't have anything to do with how they are going to interact. I didn't define it, but it's here. Activation energy is the minimum energy of collision required for 2 molecules to react. In physics terms, we think about that as being inertia. You have to overcome inertia in order for movement to happen. So activation energy is basically this hump right here, okay, that has to be overcome. If you think about, like I said, in physics term, inertia, if you go to push a car, the hardest part about pushing that car is to get it to roll initially. This is an endothermic reaction. And a potential energy scale. Okay, so I have basically the x-axis is just time or progression of the reaction, and the y-axis is the energy. So here are my reactants, and I have something called EA4, which is the activation energy of the forward reaction. And for an endothermic reaction, then the product's energy has to be higher than the reactant energy. So I knew by looking at this was an endothermic reaction because the products are at a higher energy. I'm going to show you one in which they're at an exothermic here in a second. And then you see that there's an activation energy of this reverse reaction, if I were to reverse this. And then there's also the delta H, and delta H is 83 kilojoules. Okay. Now, the delta H has a sign of either positive or negative. The pure of that sign is just to tell me whether a reaction is endothermic or exothermic. So for an endothermic reaction, delta H is positive. Exothermic, delta H is negative. Okay? And so basically what I want you to see from this graph is that the difference in this line here, the activation energy forward, would be the sum of the activation energy in reverse plus delta H. So for an endothermic reaction, that's always going to hold true. That I'm going to write across this line, EA, I'm going to say forward, is equal to the amounts of EA of the reverse plus delta H. Okay? Now, for an exothermic reaction is shown here. How do I know by looking at this that this is an exothermic reaction? Well, the way that I can tell is you see that the energy of my products is at a lower energy of that of my reactants. I still have the same components. I have EA forward, delta H, and EA reverse, but now you'll notice that EA reverse is this total line here, and then the EA forward plus delta H will add up to be EA reverse. So I can make an equation with that also, that the EA of the reverse is the sum of the EA forward, and neither one of these equations are given to you, plus delta H. And again, delta H is negative, but I'm not going to use the negative sign in my mathematics. Okay, so the negative just purely tells me that this is exothermic. So here's a energy diagram. Okay, so this comes across at 80, and if I were to draw a straight line here, and I'm going to continue this line here. Okay, and if I were to label this, if I could draw a straight line, it would look better, but this would be EA of the forward. Okay, I'm going to change colors because that way. This was a better line, is the EA of the reverse. And this last area here is delta H. Okay, so it asks what the activation energy of the forward reaction is, and so this is going to be a roughly 240 minus 80, and that's going to be 120, I think. Wait a minute. I didn't do these ahead of time like I was supposed to be. 240 minus 80. It's 160. Like I said, I didn't do that ahead of time. And then I tried to do it in my head. It's 60. The heat of reaction is roughly 160 minus 80. And is this an endothermic or exothermic reaction? This is endothermic because my ending energy is higher than my reactant energy. So this is going to be a positive 80 kilojoules. Well, I just answered that question, endothermic. And then the activation energy of reverse, I can look at the graph, but I can also tell you that from this, that the EA of reverse, if I go back to the other equation, is going to be EA forward minus delta H. So it's going to be 160 minus the 80, so it's also going to be roughly 80 kilojoules. But you could tell that from the difference between 240 and 160. And that is basically how you do a activation energy or a potential energy diagram